This is Module 5, Lesson 7. It is the last lesson in Topic A. So today we're calculating the probabilities of compound events. How can we use a tree diagram to predict the probability of more than one event occurring? That's called compound events. So a compound word is, like doghouse or hot dog or blackberry or something that has two words put together. A compound sentence, instead of saying he went to the store, period, he bought bananas, period, you would just say he went to the store and bought bananas. So compound means putting two things together. In the previous lesson, a previous lesson introduced tree diagrams as an effective method of displaying all the possible outcomes. And I just want to reiterate that all the possible outcomes, that's the sample space. And generally there's more than you think there are. Okay, a lot of kids think that if you flip two coins, you only have two possible outcomes. But that's for flipping one coin. If you flip two coins, there's four possible outcomes. If you flip three coins, there's 8 possible outcomes. If you flip 4 coins, there's 16 possible outcomes. It's usually more than kids think. Okay, so be careful when it comes to that. Additionally, in such situations, tree diagrams were shown to be helpful for computing probabilities. In those previous examples, diagrams primarily focused on cases with 2 stages. However, the basic principles of tree diagrams can be applied to situations with more than 2 stages. So even 2 stages is considered compound, but it's anything that's more 2 or more. Okay, recall that scenario with game night where B meant that they would play a board game and C meant that they would play a card game. But it wasn't just a flip of a coin, it was a 4-sided die. And then not it wasn't like half the sides meant board game, half the sides meant card game. In a minute, we're going to remember what it was that would result in the family playing a board game or in the family playing a card game. Okay, what if we didn't just do 2 nights, right? Like, what if we did Monday, Tuesday, and then added in another night, Wednesday? That would result in even more outcomes. Because when you roll the dice, you could choose board game Monday, board game Tuesday, and board game Wednesday. That would mean that you would play a board game all 3 nights. Okay? Or you could have a board game Monday, a board game Tuesday, but then a card game on Wednesday. Okay, so that's kind of the path that this tree is taking. Or you could have board game, card game, board game. Or you could have board game, card game, card game. So do you see how you follow kind of like the branches of the tree? You could have card game, board game, board game, which would be this. Or you could have card game, board game, card game, which would be this. The probabilities of those all occurring, they look to be equivalent, but if we turn the page, we're going to talk about how it wasn't always the same chance as a card game happening as a board game. So if BBB represents 3 straight nights of board games, what does CBB represent? Card game first night, board game the second night, and board game the third night. And I'll move this so it fits in. Okay, so that's what the CBB stands for, and you can underline that, CBB. Okay, list all the outcomes where exactly 2 board games were played. Exactly 2. So pause this and try on your own. Go back to the previous page. Okay, exactly 2 board games. So that would be, if we had board game, card game, that would be 1. Or I could do the card game first and the board games second. That's another one. Or there could be sandwiched in between board game, board game. Now, none of the other options show exactly 2. So that's where exactly 2 board games. So 3 outcomes that show exactly 2 board games. Okay, there are 8 possible outcomes representing the 3 nights. Are the 8 outcomes represented in the 3 nights equally likely? Why or why not? So you should know that they are not all equally represented because of that previous situation or scenario that they gave us. No, because 1 equals, and we're going to go back to this on the next part down below. 1 equals card game. Let's say rolling. Rolling a 1 equals a card game. And rolling a 2, 3, 4 equals a board game. Okay, so you don't have an equal chance when you roll the dice. Each of the sides, 1, 2, 3, or 4, is equally likely to occur, but getting a 2, 3, or 4 would be 3 of the 4 sides, and rolling a 1 would just be 1 of the 4 sides. Okay, so down below, we remember from the last lesson that rolling a 1 has a 0.25 chance, because that's 1/4. And rolling a 2, 3, or 4 gives us a 0.75 chance, because that's a 3/4. Sorry, I'm having some smartboard issues. 3/4 equals 0.75. Okay, so that's for a 2, 3, or a 4. That's because 3 of the 4 sides have the board game outcome. And like I said, that might be hard to understand, but the example I used before was that, like, maybe say the mom in the family really likes to play card games, but the other 3 family members really like to play board games. Okay, so maybe the other 3 people prefer a board game. So there we go. All right, so now below, they've calculated what the probability would be of having to play a board game all 3 nights. That would be 0.75 times 0.75 times 0.75. That's because B represents 0.75. So all you do is multiply those. I like to see them as a percent too, so just move the decimal over, and it's kind of easier to see the probabilities there, because 42% is a little less than half. Okay, and then the next question, in fact, for number 4, you can actually write C tree diagram, because we're going to do all the work there. Okay, so that is all going to be done right here. That's what we're going to do right now. We're going to calculate these probabilities. Now, you can pause it whenever you feel comfortable, okay? So pause and try when you feel comfortable. Pause and try when you feel confident or comfortable. Okay, so I'm just going to work these out. And it's going to go kind of fast. So if you want to pause it and then listen to my explanation, you can. But this is going to take a minute. So I'm going to try to do this quickly, because we did this in the last lesson. BBC would be 0.75 times 0.75, but the C is 0.25. Okay, and again, anytime you want to pause it and just try to calculate it and see if you get it right. 0.140625. And that equals about 14%. Okay, the BCB is like this. BCB, which is 0.75 times 0.25 times 0.75. If you know that mixing up the order of the factors won't change the answer, you can already tell that we're going to get the exact same answer as above. Okay, so remember, I like math, I think I'm good at math, and I still don't like to do extra work if I don't have to. But I got to copy a little more carefully because I forgot one of the numbers. Anyways, it's about 14%. Okay, BCC is right here, and B is 0.75, and then the C's are 0.25 and 0.25. Okay, so that was going to be a little lower. You should be able to catch on now that 0.75 times 0.25 times 0.25 will be a little lower, and that's 0.04. 6875, which is about, let's just call that 4.7%. You can round it to 5%, it's up to you. Okay, and then I'm not going to draw the arrows on here anymore. So let's see. The CBB would be 0.25 times 0.75 times 0.75. Again, we just did that up above. So look for patterns. Don't make more work for yourself than you have to. You can see that up above here, we did a 0.25 and 2.75. So it's also going to be 0.140625, which is about 14%. They did the next one for us, and we know it's right because look, there's 0.25, 0.75, 0.25. It should be the same answer as this one, and it is. Okay, so we can say that's about 4.7%. All right, for CCB, we've got 0.25 times 0.25 times 0.75. Again, there's another one that looks just like the one above it, so it's going to be 0.046875, or a little less than 5%. I think that's good to see because you know you don't have a very good chance of that happening. And then this last one, this should be the lowest number. There is no other one like this. It's 0.25, 0.25, and 0.25 every time. So let's see what that one equals. Did you get 0.015625, which is approximately 1.6%? Mom, sorry, you do not have a good chance of playing a card game every night. If you think about that, it's only a 1.6% chance that you, now it's still possible, of course it's still possible. That would mean that you would have to roll a 1 3 times. You would have to roll a 1 on the first roll, a 1 on the second roll, and a 1 on the third roll. It's possible, but it's only about a 1.6% chance. Okay, what is the probability that there would be exactly 2 nights of board games over the 3 nights? So exactly 2 nights of board games. Well, if you notice, let's go back here and look at our tree diagram. Exactly 2 nights of board games. Which of these have exactly 2 nights of board games? It is, I'm just going to erase these so that we can see them a little better. This one has 2 nights of board games. This one has 2 nights of board games. This one has 2 nights of board games. And that's it. Now, the other thing that you should notice is these all have the same number. Did you notice that? That was one that was repeated 3 times. So it's a 0.140625 chance 3 times. So we can actually write it like that. It's 0.140625. And there's 3 options like that. So I can multiply by 3, and that's 0.421875, which means it's about a 42% chance. And you can leave it either way, okay? We've talked about that in class. You can leave it in a decimal, you can leave it in a percent. That's okay either way. So what is the probability that they will play at least 1 night of card games? At least 1 night of card games. If you go back, you can see here that in our tree diagram, there's only one option that doesn't have at least one C in it. And where is that option? It's right here. This is the only one that doesn't have at least 1 night of card games. So instead of adding up all these, which you could add this plus this plus this plus this plus this plus this plus this. The other thing I could do is I could take this number and subtract it from 100% or 1.0. I'm going to do that. I definitely think that's a lot easier. So it's 1.0 minus 0.421875, okay, because this is all outcomes, and this is the BBB outcome. So we're really just taking that one away from 100%. And you could do that too. You could do 100% minus 42.1875%. Okay, and that leaves us with a 0.57812.5. or approximately 57.8%. Okay, in exercise 7 through 10, I want you to try this on your own. And I want you to draw the tree diagram. Now, this one is easier. This one is actually easier because it's an equal outcome for boys or girls. Okay, the probability for a boy birth is 0.5 and the probability for a girl birth is 0.5. So what are the chances of having 3 girls in a family of the first 3 births? So first draw a tree diagram, then write in the probabilities. I'm ending the video here, but you have to try this on your own, and then you'll show me that you did it and check your answers in class. Okay, so that's actually going to be the end of our lesson 7 video, and you're going to pause and try all of these on your own. Okay, that's a wrap on lesson 7.